Hi, I'm Davy Wong. I'm a student in a Master of Cryptography at the University of Bordeaux. I'm also an intern at Cryptography Services right now. And this video is going to be an explanation of two attacks on the RSA that use lattice reduction techniques. The first attack will be an attack by Coppersmith, who was the first one to find that you could attack RSA with lattices, and then we'll see how Howgrave-Graham later simplified this attack. The second attack is a Coppersmith-like attack that was discovered by Boneh and Durfee, and that was later simplified as well by Herrmann and May. So let's first briefly remind ourselves what is RSA, so we are on the same page. RSA is a public key crypto system invented 30 years ago, and it allows us to encrypt and sign. I'll just explain the encryption part because signing is pretty much the inverse operation. So first, to encrypt, you need to generate the public key and the private key associated to the public key. The public key is composed of the public exponent E and the big N, the modulus. The private key shares the same big N, the same modulus, and also has a private exponent D. To encrypt a message M, you just take your number M, you raise it to the power of E, the public exponent, you take that number modulo N, and it gives you the ciphertext. And to decrypt that ciphertext, you do the same thing but with the private exponent. This works because E and D are mutual inverse. To generate E and D, you first need to generate P and Q, the two primes, and N, the modulus, will be the multiplication of P and Q. It's easy to find D and E thanks to the primes P and Q, and that's why we say that the security of RSA is reduced to the factorization of N. So if you can find one of the prime by factoring N, for example, then you can basically find the private key if you have only the public key. There are several ways of attacking RSA, and also several goals. The first thing is to know what you want. Do you want to recover the plaintext, or do you want to recover the private key? And by the way, recovering the private key is called a total break, because if you recover the private key, then you can decrypt everything you want, and you totally broke the system. The attacks you can see in the news and the usual vulnerabilities that are being discovered are usually done in the implementation part of the crypto system, because attacking the mathematics is hard. But some researchers have thought, why not attacking a more relaxed model? A model where, for example, we have access to an oracle that gives us a part of the message, or maybe we know an approximation of one of the prime, or maybe that the private exponent is too small, and I'll define later what I mean by too small. And in those relaxed models, researchers have discovered that it's a bit easier, not that easy, but a bit easier to attack the mathematics of RSA. So let me just introduce lattice if you don't know already what it is. It's pretty simple if you think about vector spaces. For example, on the left you have two vectors, so that's the basis of our vector space. And you can do any linear combination of those, right? So you can multiply them by scalars, let's say real numbers, and then you can add the new vectors that you have multiplied together. So for example, you can take the first vector multiplied by 3.7, and you add it to the second vector multiplied by minus 11. And that gives you another vector that is still in the vector space. And you get this contiguous vector space that is made of all the different combinations of those two vectors. Now imagine that you cannot multiply them by scalars, by real numbers, and that you can only multiply them by integers. That means that you still have the same basis, but you can only do linear combinations in the integers. It gives you just a set of points in space, and this is a lattice. It is a discrete space. That means that if you take any point in that space, you will be able to find a sphere centered around that point that contains only that point, which is impossible to do in the real number space, for example. So a lattice is basically this. It's a space that is spanned by the linear combination of some vectors, but in the integers. And that is interesting because in cryptography, we usually play with integers. And we want to find a mathematical model that is close to what we're doing, right? And the interesting part about the lattice is that we have all those tools, especially that tool that was created by three guys whose first name starts with the letter L, so it's called LLL. And this algorithm allows us to find a smaller basis if you give it a basis of a lattice. So on the left you have this lattice with the two vectors, like a random basis, two vectors. And what LLL does is that it finds two new vectors that are smaller and that span the same lattice. So the lattice doesn't change, but the basis is shorter. Then we'll see later why it helps us, but the basic idea is that you feed that algorithm a basis, gives you a new basis with shorter vectors, and you have an exact formula for the upper bound of those new vectors, and that will help us a lot. So the first attack we'll see is Coppersmith attack, and he's the first one who used the lattice to attack RSA. So he's thinking about the model, the initial model, where you're just trying to find a message out of the ciphertext and the public key. So you know C, you know E, you know N, but you don't know M, and you're trying to find that. And that's hard. That's very hard. So what if you knew a part of the message? What if the message was always something like the password today is, and then the password? That would mean that here in this equation, you know M0, but you don't know X0, and you're trying to find X0. And you can transform that into an equation, right? So it doesn't really, it's not very important to understand how you translate that to an equation, but if you want to take time to understand, you can pause the video and just understand that. But the idea here is that Coppersmith gives an algorithm to find the roots of a polynomial modulo n when the roots are small enough. And by finding the roots, you find the solution of our problem. So finding the roots of a polynomial modulo n is kind of difficult. We don't really know how to do it. But if we have a polynomial over the integers, and which has its roots over the integers, then we know how to do it. We have techniques for that. We can, for example, factor the polynomial and just read out the solutions. But modulo n, not so much, not so easy. So the first idea of Coppersmith was to find another polynomial, g, here, that has the same roots as our problem f, but over the integers. And then it will be easy to find, right? So how do we find that new polynomial with the same root but over the integers? Well, Howgrave-Graham, that simplified the attack a few years later, gives us this beautiful theorem. So imagine you have this g, this polynomial which has the roots we're looking for, modulo n, and we know that this root is small enough, it's upper bounded by big X, right? So we know an upper bound for this root. And Howgrave-Graham tells us that if we add a second part to that polynomial, this equation that is the norm of the new polynomial made out of the first polynomial and the upper bound, and if this norm is upper bounded by a specific number, then we know that this polynomial has its roots over the integers. And so we can calculate its roots over the integers instead of modulo n, because it's easier. So how do we find that kind of polynomial? Well, the idea here is that we could generate several polynomial that have the same roots as our problem f, and combine them using linear operation over the integers. So we keep the roots. So we have a bunch of those polynomials creating a new polynomial with the same roots, and which has small coefficients. So if you take the norm of this new polynomial, you will get something small enough that it will be upper bounded by this. Okay, but this is hard because we don't really know how to generate all those polynomials which has the same root as our problem. What we could do is that we could generate all those polynomials that have the same root but modulo n to the power m. And this is easier because we have a lot of tricks, and you'll see later how we can do that. But basically we can multiply by n to the power m, or we can raise our polynomial to the power m and stuff like that. And so our problem is now to find a polynomial that has the same root as our problem, but modulo n to the power m, and which has small coefficients, so that the norm of this new polynomial is upper bounded by this. And then we know we can find the roots over the integers. Okay, so how do we combine those polynomials together? That's where LLL, the reduction technique we just saw for the lattices, is very, very, very useful. So this fantastic technique comes with two things that are of interest for us. It only does integer linear operation. As I said before, if you give it a basis, it changes the basis, but it keeps the same lattice. And that's because it only does integer linear operations. And if you do integer linear operations on polynomials, you keep the root. You preserve the root. The second thing that is good for us is that LLL gives us shorter vectors, and especially one vector that we'll call the shortest vector of the new basis. And if you remember, we have an upper bound on all the new vectors of the new basis that LLL finds, and especially on that first vector here. So I didn't tell you earlier how to do those polynomials, how to create all those polynomials which have the same root as our problem, but modulo n to the power m. So here is how. Again, if you want to understand exactly how they have the same root but modulo n to the power m, you can pause the video. I'll just explain what they achieve. First, so they have the same roots, but they also introduce a new monomial. Each iteration of this series of polynomial introduce one new monomial. And so this is very, very useful, because when we'll insert all those polynomials into our matrix that represent the basis of the lattice, it will give us a triangular matrix. And now if we want to know the determinants of that matrix, it's just the product of all the terms of the diagonal, right? And as we've seen before, the determinant is the important part of the upper bound of our shortest vector after LLL. So let's go back to our diagram. So we have our problem, right, f, and we're trying to find the roots, modulo n. And to do that, we're trying to find another polynomial which shares the same roots, but modulo n to the power m. And if that polynomial respects the second point of a Howgrave-Graham, these inequalities, then we can find the roots over the integers, okay? And we said that we could do that by combining a lot of polynomials. So that's our new diagram, okay? And really quick, we generate a bunch of polynomials that have the same root as our problem f, but modulo n to the power m. We create a matrix with all those polynomials that will be the basis of our lattice. We give that basis to LLL. It gives us a new basis, and the shortest vector is actually the polynomial we're looking for. But if you look closely to the diagram, you can see that we're fitting it f like functions of x multiplied by our big X, which is the upper bound of our roots. So why is that? So let me explain. Remember the property of LLL. We know that the new basis after LLL will have a shortest vector that will be upper bounded by the determinant and some number, right? We know that. And we also want to find a new polynomial that respects that formula, the second point of Howgrave-Graham's theorem. How do we combine these two? Well, let's just say that the polynomial that we're looking for is actually the shortest vector. And that's it. That's all we have to do. So if we look back at our diagram, instead of giving it the polynomials, we give it new polynomial, like the composed polynomial with the upper bound x of the roots, so that LLL will give us such a polynomial. And when we have this kind of transformed polynomial, it's actually very easy to just transform it back to just g of x. Okay, cool, great. We know how to do our matrix. We know how to do everything. But for what value of x, for what kind of roots, and what is that m that we use in our algorithm? So to do that, we have to understand that from those two inequalities, Coppersmith found that the determinant was bounded by this formula, which you can simplify as this formula because some of the terms are just negligible compared to n. And you have a theorem which says exactly for which value of m, for which value of n also, and the dimension of our matrix, and for what value of x, big X, so for what kind of a small roots, we have this method and we can find the roots. This is also more than that. Coppersmith gives a more general kind of theorem where you can see he uses b as modulo in the polynomial when b is greater than n raised to the power beta. And this is because you can apply this technique even if you don't know the modulo. And this allows us to attack RSA under different angles. For example, if you have an approximation of one of the prime, you can transform that problem into a polynomial modulo one of the prime. And if you don't know that prime, it doesn't matter because you can still use that algorithm. But I won't explain that in that video. If you're interested, you can look at different articles that I'm linking under that video. So much later, in 2000, Boneh and Durfee found an attack on RSA using a Coppersmith-like attack. So we saw Coppersmith's theorem, that is a technique to find small roots of some polynomials, modulo n. And Coppersmith also gave heuristics. So not a theorem, he didn't prove anything, but he gave like a general technique to attack polynomials with multiple unknowns. And Boneh and Durfee used that on bivariate polynomials to attack RSA. So let's see how. So now it's gonna be more interesting because we're gonna see a total break. So we're trying to find the private key out of the public key. So if you remember, to generate the private key and the public key associated with each other, we needed to first generate two primes, P and Q, right? And RSA works because you have this equation. You have E and D mutual inverses modulo the totient function, right? Euler's function. If you don't know why, I advise you to check Wikipedia and some group theory. It's pretty easy to get into, and it allows you to understand a lot of mathematics behind RSA. Anyway, so you transform that into the integers and you remove the private parts by putting the equation modulo E, the public exponents, and then you have this equation that has two unknowns. So here k could be x and minus p minus q could be y. And those are our two unknowns, and we have our polynomial, and we're trying to find the roots modulo E. Okay, so we just transformed our problem to a polynomial with two unknowns, and if we find the roots of that polynomials modulo E, then we find the private key. It's not that important to understand exactly how we transform our problem into that polynomial. Know that the technique we're gonna see is to find the roots of a bivariate polynomials efficiently when it's modulo some number. And if you want to understand how we transform that problem into that polynomial, just pause the video and take a look at it. So what's pretty cool with Coppersmith is that we can use this exact theorem for bivariate polynomials. So here you have Howgrave-Graham for bivariate polynomials, exactly the same thing, except it's not modulo n to the power m, it's modulo e raised to the power m this time. And we have an upper bound on the root x and an upper bound on the root y. Okay, so we can use basically the same technique as earlier with this time a bivariate polynomial, except that at the end when we find the new g that has the roots over the integers, we have a problem. Imagine a polynomial like x equals y. You can have an unlimited, infinite number of solutions. And that's why for such polynomials you need at least two independent polynomials to be able to find a solution. And how to find those two polynomials? Well, if you remember the property of LLL, we have an upper bound on all the new vectors of the basis, the new basis, and we just take the two shortest vectors. And our diagram becomes this diagram where we just use the two shortest vectors, we transform them back into G1 and G2, and we can use, for example, the resultant algorithm to find the roots over the integers, or we can also use Grobner basis. I won't explain that in that video, so if you want to know exactly how that works, you can look for that yourself. So with this technique, you calculate the bounds like earlier, and you arrive to a point where you know you can do this. You can find the private key if the private key is smaller than n raised to the power 0.28. Alright, you have a bound on the private key, and you know that if the private key is small enough, you can find the results. And Boneh and Durfee asked themselves, can we do better? And yes, they could, because if you look at that matrix, so that's the matrix that we use as basis for the lattice, we're gonna feed LLL, and those are the series of polynomials in the rows. And we can see that in the diagonal, some of the terms are damaging. They are too big, and the bigger they are, the bigger the determinant will be, and the worse the upper bound on our shortest vector will be. Remember, we're trying to find a new polynomial with short coefficients, so with a small norm, so we can find the roots over the integers. So we have to find the smallest determinants possible for it to work on this matrix. And those polynomials here are damaging the determinant. So why not remove them? So we remove them, and now we have a rectangular matrix, and so we cannot calculate the determinant, and now it becomes quite hard to know exactly what will be the upper bound on the new two shortest vector of the new basis. And Boneh and Durfee did that by inventing the concept of geometrically progressive matrices, but this is a bit complicated, and fortunately Herrmann and May, a few years after, found a technique to avoid all this complexness with the rectangular matrix. They call that unraveled linearization, and it's just a substitution. You take your polynomials, your problem, and you substitute 1 plus x multiplied to y by u. And you do that in all the polynomials you generate, and it gives you a new matrix, a new basis with the substitution, and actually the new matrix is triangular, and that's wonderful because we can calculate the determinant easily. And actually doing the substitution here at the beginning, we can do the substitution back when we finish our problem, and it doesn't change anything, it just changes our matrix. And we can calculate the determinant, and we can calculate the bounds more easily. And Boneh and Durfee found that by doing that, by removing the damaging polynomials from our list of polynomials, we could find the private key if the private key was smaller than n raised to the power 0.292. and that's called the Boneh and Durfee bound. So I personally coded the two attacks, Coppersmith attack and Boneh and Durfee attack. So if you want to dig more into this and you want to have a better understanding, you can go to GitHub and you can find my repo, and you can try to use and you can try to read the code, and maybe that will help you a bit more. Just informative results. Coppersmith is pretty fast, yields good results every time. It's a theorem, so I know every time it's gonna work, and I never took more than 1 second, whatever the size, to find the results. Boneh and Durfee is more complicated. So here delta is delta is in the formula, n to the power delta is supposed to be bigger than our private key d. And if our private exponent, for example, is smaller than n raised to the power 0.27, then we took approximately 2 minutes to find the solutions. If we go bigger than that, if our private key is bigger than that, then it takes way more time, and I didn't have enough time with my small machine to yield any good results. So this is because when you have bigger values for the private key, you have to increase the dimension of the lattice, and the complexity of the algorithm is dominated by the complexity of LLL. So the bigger the lattice, the longer LLL will take time to compute the new basis. So theoretically, we could compute the private key for bigger private keys, but it takes a long time. So Boneh and Durfee arrived at a conclusion with that result of 0.292. But they thought it was an unnatural result, and they thought that you could find a better result, but in 15 years nobody has found such a result. And actually a team of Chinese researchers at Tsinghua, Beijing University, has found that, and I don't know if the paper is legit, I didn't really look into it, but apparently the bounds were miscalculated and you cannot find private keys for such a big number. If you want to find big private key and this technique is taking too much time, what you can do is you can do the Boneh and Durfee attack for a small value of d, and if it doesn't find any results, then you know d is bigger, and you can try to do an exhaustive search, a brute force, to find the value of the private key. So now is the end of my video. I hope you understood everything. This is only my second video trying to explain an article. In this video, actually multiple articles, and I will be clear in the next videos, and I hope you could get a better understanding of those two attacks thanks to me, thanks to that video. Alright, so stay tuned for more videos, and you can check my blog also in the links below that video. Thanks guys, cheers.